Welcome back to QHSE Talks, your destination for taking safety knowledge from theory to real-world impact. Today, we're diving into a critical topic from David Yates's Safety Professionals Reference and Study Guide, particulates and gases. If you think safety is just about checking boxes or memorizing rules, this episode will show you it's so much more than that. Every day, workplaces are filled with invisible hazards, gases, vapors, dusts, fumes, and fibers that you can't see but can have serious effects if not properly managed. Understanding these hazards isn't just academic, it's the foundation of effective HSE practices and the backbone of professional safety decision-making. It all starts with chemistry. Knowing the atomic makeup, bonding behavior, and reactivity of a substance allows you to predict how it behaves in the air. Concepts like atomic mass, valence electrons, and moles aren't just for exams, they give you the tools to quantify exposure and risk. Then we move into gas behavior. Laws like Boyle's, Charles, and the ideal gas law might sound technical, but for safety professionals, they're indispensable. They explain why pressure builds in confined spaces, why temperature changes affect vapor concentration, and why ventilation and control systems must be designed with precision. This is where your CSP level understanding elevates safety from guesswork to science. Next comes measuring and classifying airborne hazards. Dust, fumes, mists, fibers, and vapors each have unique behaviors, and exposure metrics like time-weighted average, TWA, standard temperature and pressure, SDP, and permissible exposure limits, PELs, allow HSE professionals to know exactly when action is needed. Flammability calculations give another layer of control, helping ensure that workplace concentrations never reach dangerous levels. Think of it this way. Chemistry tells you what the substance is, gas laws tell you how it behaves, and exposure limits tell you when it becomes a problem. Mastering these principles means you're not just enforcing rules, you're actively managing risk and protecting lives. And this leads us perfectly into today's discussion.
And this is where the safety professional's role fundamentally changes. Understanding this material elevates you. You go beyond being a simple compliance checker.
Right.
You become the expert who can truly quantify the risk. You're able to look at a highly corrosive, very common industrial chemical like sulfuric acid, which will be our case study today, and understand its precise mass, the concentration ratios, and the exact weight contribution of its elements.
All from that little formula.
All from the formula. This knowledge is the basis for all quantification and control measures in the field, period.
Okay, let's unpack this then. We're going to start at the absolute foundation, the core of everything we manage, from gases to particulates. We're starting with the anatomy of matter, atoms, and ions.
The very beginning.
Every substance you encounter, the air you're breathing, the steel in a building, or a vat of highly reactive acid, it's all composed of atoms. And to understand the atom, we have to start at its core, that very heavy, dense center, the nucleus.
Think of the nucleus as the sun of this little atomic solar system. It holds virtually all the mass of the atom.
And it's made of two things.
Two primary subatomic particles, yes. You've got the protons, which carry a positive electrical charge.
Okay.
And then you have the neutrons, which, as the name suggests, are electrically neutral.
And they're just locked together in the center.
Incredibly tightly. This gives the nucleus that net positive charge, and it's what defines the element's mass.
And orbiting around this massive positive core.
That's where you find the electron cloud. These are incredibly lightweight, super fast-moving particles that carry a negative electrical charge.
They don't just fly off.
No, they orbit the nucleus in specific energy shells, or, well, clouds. The forces at play here are just crucial. Electrons don't just drift away because they're held in that orbit by a powerful electromagnetic force. It's the simple attraction between the positive charge of the protons in the nucleus and the negative charge of the electrons.
So positive and negative attract, it's that simple.
It's that simple, but that intricate balance is what keeps all of matter stable And this balance defines the whole concept of the neutral atom.
Okay, so let's talk about the neutral atom's balance. This sounds like a key concept.
It is the element's identity statement. The most important number on the whole periodic table is the atomic number.
Okay.
That number is always equal to the number of protons in the nucleus. Always. If you change the number of protons, you have entirely changed the element. You turn carbon into nitrogen, for instance.
So the proton count is like the element's immutable DNA. You can't change it.
You can't.
Yeah.
Not with chemical reactions anyway. So in a neutral atom 1 that doesn't have any overall electrical charge, that positive charge from all those protons has to be perfectly offset by the negative charge from the electrons.
Which means they have to be equal.
The number of electrons equals the number of protons. Exactly. So if you know the atomic number, you instantly know both of those counts. It's that straightforward.
But there's a third part, the third component of the mass, the neutrons. How do we figure those out?
Right. To calculate the number of neutrons, you take the element's atomic weight, which is the total mass of the nucleus, and you just subtract the atomic number.
The proton count.
The proton count. So atomic weight minus atomic number gives you the number of neutrons.
Okay, so if an element has an atomic weight of, say, 14 and an atomic number of 7...
Then it must have 7 neutrons.
Yeah.
14 minus 7.
That simple subtraction is absolutely essential knowledge, even if you're not dealing with, a core nuclear hazard or something.
But you might be wondering, why is the neutron count critical for the safety professional?
Oof.
I mean, if the bulk of your work is with industrial chemicals, why does this matter?
Yeah, that's a good question.
It's because you might encounter different isotopes of elements.
Isotopes, right.
Isotopes are just atoms of the same element, so they have the same number of protons, but they have different numbers of neutrons.
Which means they have different atomic weights.
Exactly. And while the standard atomic weight we see on the periodic table gives us a good average for our calculations, understanding that neutron variation can be the difference between a stable material and one that might, say, exhibit low-level radioactivity or just behave differently under high-energy conditions.
So it's about recognizing the variation within the species, so to speak.
Very good way to put it.
But the real action in chemistry, I guess, happens when the atom gives up this neutral stability.
That's right.
Which brings us to the creation of ions, these charged atoms that form the basis of salts, acids, and bases.
Atoms are always seeking the most stable configuration they can get. Often that means mimicking the full outer electron shells of what we call the noble gases.
Like neon or argon.
Exactly.
Yeah.
And to do that, they have to either gain or lose electrons, and that results in a charge imbalance.
Okay, wait a second. If the atom loses an electron, doesn't that change its identity? We just said changing the proton count changes the element entirely. Why is changing the electron count okay?
That is a crucial distinction and a great question. The protons, locked away in the nucleus, are inviolable for chemical identity. They define the atom spot on the periodic table.
Okay.
Electrons, however, they're in that outer cloud, the valence shell, and they are highly exchangeable. So when an atom gains or loses electrons, its chemical identity, the element, stays the same.
But its electrical state changes.
Its electrical state, and critically for us, its reactivity changed dramatically.
So the creation of an ion is all about manipulating that unstable electron cloud on the outside.
Yes.
Let's focus on the positively charged ions, or cations, since they're so common in industrial compounds like, say, sodium chloride.
A cation is created when electrons are lost. Since you've removed negatively charged particles, the number of positive protons now outweighs the number of negative electrons.
So you get an overall positive charge.
Right. Take sodium NaM, for example. It has one single electron in its outer shell that it is desperate to get rid of to become stable.
Because it's much easier for it to just drop one electron than to try and gain 7 more to fill that shell.
Precisely. So it drops that single electron and it achieves stability. But how do we calculate the exact number of electrons left in that resulting sodium ion, which we write as Na+?
Right, with the little plus sign.
We use that simple rule derived from the neutral atom balance. Sodium's atomic number is 11. That means it has 11 protons.
Always.
If it loses one electron, which results in a +1 charge, you calculate the remaining electrons by subtracting the charge from the atomic number. So 11 minus 1.
It now has 10 electrons.
And it has 10 electrons. That calculation of atomic number minus charge is absolutely foundational.
So the takeaway here is that you need to be able to look at any industrial chemical that involves this kind of ionic bonding-like hydrochloric acid reacting with sodium hydroxide and just quickly determine the functional state of the particles involved.
Yeah.
Knowing that Na+ is just a stable particle with 11 protons and 10 electrons gives you a deep insight into how it's going to behave. It's so much more than just memorizing a symbol.
And understanding how these atoms stabilize themselves through this exchange is the entire basis for chemical bonding. And once atoms bond, they form molecules, and that requires a completely new language.
Right. Okay, so that leads us into our next section, the language of chemistry formulas and conservation.
The grammar of molecules.
Once atoms combine, we need a universal way to write down exactly what they made. And this brings us to chemical formulas as shorthand. It's really the most concise way to express the composition of a molecule and its potential for reaction.
It's just an exercise in efficiency. I mean, we don't write out long descriptions. We use symbols and numbers.
For example,
take hydrochloric acid, a very common, highly corrosive lab acid. Instead of writing 1 atom of hydrogen chemically bonded to 1 atom of chlorine, we just write HCl.
And that notation immediately tells you the qualitative components, H and Cl, and the quantitative ratio, 1:1.
Exactly. The system really shines, though, when you're describing more complex molecules, like our central example for today, sulfuric acid.
Its formula is H2SO4.
And here, the use of subscripts is just paramount. Subscripts tell you the precise count of identical atoms in that one molecule.
So if we analyze H2SO4, that little 2 next to the H tells us we have 2 hydrogen atoms.
Correct. And the fact that there's no subscript next to sulfur, the S, implies there's just 1 atom of sulfur.
And the 4 next to the oxygen means 4 atoms of oxygen.
That's it.
So that single molecule of sulfuric acid is a 7-atom structure, 2 hydrogen, 1 sulfur, 4 oxygen. Why is knowing the count of those constituent atoms so vital for a safety professional?
Well, because it defines everything. It defines the molecular geometry, the potential reaction sites, and most importantly for our purposes, the entire mass budget of that molecule.
Yeah, mass budget. I like that.
When we move to the mass calculations in the next section, we absolutely have to know exactly how many atoms of weight 16 oxygen, and atoms of weight 1 hydrogen we are counting. The formula is the structural blueprint for quantification.
Okay, but the formula only describes the static molecule. What happens when we mix chemicals and, start a reaction? They have to follow the most fundamental rule in the universe.
The immutable rule, the law of conservation.
This is chemistry's big, non-negotiable rule.
It absolutely is.
Yeah.
Matter can be neither created nor destroyed.
Yeah.
You cannot start a chemical process with 100 grams of material and end up with 101 grams, or, for that matter, end up with 99 grams.
So you can't lose a gram either.
You can't.
Yeah.
The atoms simply rearrange themselves into new molecules.
It sounds kind of obvious when you say it like that, but this law has profound practical consequences that dictate how we manage chemical processing in an industrial environment.
Oh, absolutely. The application to equations means that for any chemical reaction equation you write, reactants A plus B, yield product C plus D, the total number of atoms of each individual element has to be identical on both sides of that equation. If you start with 3 chlorine atoms on the reactant side, you must end with 3 chlorine atoms on the product side, regardless of which product molecule they end up in.
This is why we have to balance chemical equations. It's not just some academic exercise. It's a mandated requirement of physics.
It is.
But what does a safety professional actually need to do with a balanced equation? What's the practical use?
The balance is the foundation for predicting mass and volume. Imagine you're overseeing a reactor where 2 substances combine to produce a dangerous byproduct, maybe a flammable gas, or just a high volume of a liquid product.
Okay.
If you know the precise mass of the reactants you're putting in, the law of conservation dictates that the total mass of the products coming out has to be identical to the gram. If that reaction happens in a sealed or closed vessel, this allows you to calculate the precise volume of gas that will be generated, because mass ties directly to volume for gases. And therefore, you can design the pressure relief system or the containment unit to handle that exact predicted load.
So a failure to balance the equation correctly isn't just a math error.
No.
It could be a catastrophic engineering failure that leads to overpressurization, a rupture, or an explosion, all because you underestimated the mass of the product you created.
That is precisely it. The law of conservation is the bridge that allows you to confidently use stoichiometry, which is really just a fancy word for using these precise weight rules to make sure our reactants and products balance out.
And that informs critical control measures.
Yes, like sizing ventilation capacity or designing the safety margins for a pressure vessel. It all comes back to that balanced equation.
We've identified the parts, the atoms, and we've described the formula. Now we move to putting a truly measurable concrete weight on that whole molecule.
This is where it gets really practical.
Section 3. Quantifying chemical hazards molecular weight calculation. In industrial hygiene and exposure assessment, numbers like parts per million or milligrams per cubic meter are everything.
They're the currency of the profession.
And these calculations are fundamentally based on the mass of the substance. But before we can weigh a compound, we have to know the standard weights of its basic components. And this leads us to the importance of atomic weights.
Atomic weights are the standardized relative weights of the elements, and they're based on the carbon-12 scale, while the periodic table gives you these highly specific, long decimal numbers.
Right.
For rapid field assessment and standardized calculations, safety professionals are really expected to internalize a few key, slightly rounded weights for the most common elements they're going to encounter.
It's a bit of a memory test, then.
It is, but it's a necessary one.
Okay, let's lock in those critical values cited in the reference material. These aren't just useful. They have to be second nature to a safety professional.
They do.
First, sodium, nay, that's 23.
23.
Hydrogen H is 1.
The easiest one. Just one.
Carbon, C, is 12.
12.
Nitrogen N is 14.
14.
And oxygen O is 16.
16. Notice how clean those numbers are. They're derived from the total average mass of the protons and neutrons of that element's naturally occurring isotopes.
So knowing these numbers means you don't have to pause in a critical moment to look at a table.
You can immediately translate a chemical formula into a mass value. It's about speed and confidence.
And once we have those baseline weights, we can perform what is probably the most important calculation in this chapter, determining the molecular weight of a compound. We're going to use the detailed example from the guide. The detailed calculation for sulfuric acid, H2SO4.
This calculation really demonstrates the meticulous nature that's required.
Yeah.
You have to multiply the atomic weight of each element by the number of times it appears in the formula, its subscript, and then sum all the results.
And precision is key here.
Precision is key. So for sulfur and oxygen, we're going to use the more precise values provided in the source material for maximum accuracy, which is standard practice for highly regulated industrial chemicals.
Okay, let's break down the contributions element by element. Let's start with hydrogen H. The formula is H2SO4, so we have 2 atoms of hydrogen, and its atomic weight is 1.
So the contribution for hydrogen is simply 2 atoms times 1. Its atomic weight equals 2.0. That's hydrogen's minimal mass contribution to the molecule.
Easy enough. Next up is sulfur, S. We have 1 atom of sulfur in the formula. The reference guide provides the specific atomic weight for sulfur as 32.066.
Right, so sulfur's contribution is 1 atom times 32.066, which is just 32.066. And you can see it's already significantly heavier than the hydrogen component.
A lot heavier. Finally, oxygen, OO. We have that subscript 4, so 4 atoms of oxygen. The precise atomic weight given is 15.9994.
Okay, so oxygen's contribution is 4 atoms times 15.9994. That comes out to 63.9976.
Wow.
Yeah, as you can see, this one element, oxygen, contributes by far the largest amount of mass to the entire sulfuric acid molecule.
Okay, now we need to determine the total compound weight. We just sum those 3 component masses. So 2.0 from hydrogen.
Plus 32.066 from sulfur.
Plus 63.9976 from oxygen.
And the total compound weight is 98.0636.
98.0636.
That number, 98.0636, is effectively the weight of the danger we are assessing. This is a vital metric. It's the one that every safety professional must carry forward into every single exposure calculation. It's the anchor point.
But 98.0636 is a relative unit of mass, right? To translate that into a measurable, usable quantity of material, the grams we can actually put on a scale, we need to introduce the concept of the mole.
Right. And this is often labeled as, dense or difficult in textbooks, but it really doesn't have to be.
So how should we think about it?
Let's just strip away the textbook definitions about carbon-12 and Avogadro's number for just a moment. Think of the mole as a universal counting unit. It's like a baker's dozen, but for atoms.
A baker's dozen is always 13.
And a mole is always 6.022 times 10 to the 23rd particles. It is simply the required bridge between the microscopic world of atomic weights and the macroscopic world of laboratory or industrial mass measurements.
So the magic of the mole is this functional connection. The calculated molecular weight of a substance, when you express it in grams, is exactly 1 mole of that substance. Is that right?
That is precisely it. If we calculate the molecular weight of water, H2O, as approximately 18, then 1 mole of water weighs 18 grams.
Simple.
Applying this to our case study, the molecular weight of H2SO4 is 98.0636. Therefore, we can confidently state that 1 mole of H2SO4 would weigh 98.0636 grams.
That is the simple, crucial takeaway. The molecular weight value lets the industrial hygienist convert a known volume of a gaseous contaminant into a mass concentration, like milligrams per cubic meter.
Or convert a mass of spilled liquid into a molar concentration for calculating reaction kinetics.
So without the mole, this quantified weight just remains kind of meaningless in a safety context.
It's the conversion factor that makes all exposure and dosage calculations possible. And now that we know the total mass of the molecule, we can move immediately to the final, highly practical calculation, determining the relative contribution of each component.
Okay, section 4, practical application percentage of element in a compound. This moves us firmly into risk analysis. If you're dealing with a material, knowing its total weight is step 1.
Step 1.
Step 2 is determining how much of that total weight is comprised of the element that is actually causing the hazard, whether that's a toxic metal, an oxidizing agent, or a flammable component. This defines the safety professional's need for percentages.
Yeah, and this is so important. If you are assessing the exposure risk for a compound, you rarely regulate the overall molecule. You regulate the hazardous element within it.
Can you give an example?
Sure. OSHA sets permissible exposure limits, PELs, for elements like sulfur dioxide, not necessarily for every single complex compound they might be bound up in. So we have to quantify the exact percentage contribution of that regulated substance within the larger structure.
And it's also useful for material substitution.
Oh, vital. If you're replacing a substance that's 50% toxic with one that's only 5% toxic, you need this calculation to justify that change.
And because we were so meticulous in the last section, we already have all the numbers we need to determine the percentage composition by weight. Let's detail the straightforward method for calculation using our H2SO4 figures.
The method is just a simple ratio. You take the total weight contribution of the specific element you're interested in, you divide it by the total molecular weight of the compound, and then you multiply by 100%.
Okay, let's demonstrate this crucial step. Let's calculate the percentage of 2 elements in sulfuric acid. Hydrogen, which we know is the smallest contributor, and oxygen, the largest. Our total molecular weight is 98.0636 grams.
Let's start with hydrogen. We established that the total mass contribution of the 2 hydrogen atoms was exactly 2.0 grams.
Okay, so the calculation is 2.0 grams of hydrogen divided by the total 98.0636 grams, and then times 100%.
Exactly. That calculation yields 2.0396 and so on, which we can just round to approximately 2.04%.
So that tells you that for every 100 grams of pure sulfuric acid, only about 2 grams are actually hydrogen.
Right, and while that percentage is low, its presence is absolutely crucial for the acid's properties. It's what makes it an acid.
Now let's look at the dominant component, oxygen. We calculated that the 4 oxygen atoms contributed 63.9976 grams to the total molecular weight.
So the percentage of oxygen is 63.9976 grams of oxygen divided by the total 98.0636 grams times 100%.
That works out to roughly 65.26%.
Yeah.
That is incredibly revealing. Over 2/3 of the mass of this highly corrosive, dangerous acid is actually just oxygen.
And this number isn't just trivia. It immediately informs your risk assessment. Since H2SO4 is so rich in oxygen, we know it's a powerful oxidizing agent.
What does that mean in practical terms?
This high oxygen content changes the way we have to store and handle it. It requires specialized, isolated storage away from anything flammable or combustible.
Because the acid itself can fuel a fire.
It can supply enough oxygen to fuel an existing fire or to react violently with what are called reducing agents.
That's the utility of the chemistry. By translating the atomic count into a percentage mass, we move directly from a theoretical formula to a very specific practical control measure about storage, segregation, and fire suppression strategy.
Let's do the last one too. Consider the sulfur component. We calculated its contribution as 32.066 grams.
Okay, so calculating its percentage. 32.066 grams of sulfur divided by the total 98.0636 times 100%.
That's approximately 32.70%.
So about 1/3 of the molecule.
About 1/3. Now, if this acid decomposes, say in a fire, that sulfur is released. It quickly forms hazardous sulfur dioxide or sulfur trioxide gases. Knowing that roughly 1/3 of the molecule's mass is dedicated to that sulfur backbone helps safety professionals predict the maximum potential release concentration of sulfur compounds in a loss of containment scenario.
This whole exercise, from counting subatomic protons all the way to calculating the final weight percentage, is the required foundation for all quantitative industrial hygiene.
It really is. It ensures that when you manage exposure, you are doing so based on the precise, measurable composition of the material you're working with.
Okay. We've completed a massive deep dive today, moving from the microscopic to the measurable. We started by defining the atom, understanding that the proton count is the element's identity.
And that the manipulation of electrons creates ions that drive all chemical reactivity.
We then mastered the shorthand of chemical formulas, using those subscripts to count atoms, and affirmed chemistry's golden rule, the law of conservation.
Which allows us to balance reactions and predict mass generation in closed systems. A critical skill.
Finally, we translated theory into practice. We used critical memorized atomic weights to meticulously calculate the molecular weight of sulfuric acid, H2SO4, determining that 1 mol weighs 98.0636 grams.
And we leveraged that total mass to calculate the percentage composition, finding that roughly 65% of the molecule is oxygen, which immediately informed storage and fire risks.
What's the key takeaway here?
The key takeaway is this. This level of quantification is your competitive advantage. It's the ability to calculate mass and percentage composition that allows you to confidently move into the regulatory and control engineering aspects of the job. It ensures your exposure assessments are based on precise chemical reality.
So you're no longer just looking at the hazard warning symbol on the drum.
You're looking at the molecular reality that generates that warning. You understand the why behind the label.
So let's leave you with one final thought to consider as you process all this foundational knowledge. We've established the chemical facts for sulfuric acid. Its mass is 98.0636 grams per mole. If this mass is universal, how does the physical state of these calculated materials fundamentally change the way a safety professional must implement controls and protect workers?
Think about the implications of that. 98.0636 grams of liquid sulfuric acid requires dermal protection, gloves, face shields, and containment berms for spills.
Okay.
But if that same 98.0636 grams becomes an aerosolized particulate mist...
Like from a high-pressure spray leak.
Exactly. Now, it requires respiratory protection and significant ventilation controls. And if it becomes a gaseous decomposition product in a fire, it requires even stricter air monitoring and possibly supplied air respirators. The chemistry stays the same, but the calculated mass must be addressed by completely different engineering controls.
Depending on whether that mass is a liquid, a solid particulate, or an invisible gas.
It's the meeting point of chemistry and control engineering. The math is universal, but the application of safety controls is specific to the physical state.
Something critical to ponder until our next deep dive. Thanks for joining us.